I love that movie. Okay. Um, Now, you might be saying to yourself something along the lines of, huh? That's okay. The quantum world is very strange, and that's one of the reasons that I show you that video. That's actually like, it's kind of a cartoony and it's very sensationalized, but that is based on real experiments that were done that physicists just it like blew everybody's minds. Famously, Einstein didn't really believe in the quantum world, and it's a little confusing. So I'm going to walk you through some of it and see how we're going to use it. But the bottom line here is that electrons can be treated like particles and waves, and this was proposed by Louis de Broglie. All right. So a lot like light could be treated like a wave or a particle. Electrons and other small particles can also be treated like a wave. Okay, now there was also this observation issue, right? That when they observed the electrons, they went back to behaving like particles. All right, and actually, this shouldn't really surprise you that much because by observing something, what that means is light has to be like photons have to be bouncing off that electron and coming back to the observer, which means that some sort of energetic particle has to interact with that electron in order for you to see it. Okay, now that's going to change the electron, and you know that because we talked about it last class. All right, so Heisenberg used this to state that it is impossible to know the position and the velocity of an electron at the same time. Okay, and that's the Heisenberg uncertainty principle. Another scientist, Schrödinger, said, okay, well, people have tried to describe electrons as particles, and the models kind of break down. All right, that's what happens. So what if I tried to describe electrons as a wave? Can that work? And so he comes up with a series of mathematical equations, and the math is very complex. Okay, it's like multivariable calculus. There are like time dimensions. There's a lot of weird stuff in there. All right, so we're not going to worry too much about the math, but solutions to Schrödinger's equations are important. They're known as wave functions. Okay, and what wave functions do, and I'm going to walk through a simulation as well that's going to kind of put a good spin on this. But these wave functions give a probability of finding an electron at a given place around the nucleus, and we're going to talk more about that in a second. So the important thing to keep in mind here is electrons do not orbit. Okay, that just, it doesn't really work. Instead, they exist in regions of 3D space, okay, about the nucleus. And we call these regions orbitals. So we're going to be talking a lot about orbitals today. So here's the Bohr model, which we talked about, and the Bohr model is incorrect, okay? And what seems to be better is describing electrons as waves and wave probabilities. So what do I mean by like a probability map or something like that? Okay, so a good analogy here is a dartboard. Okay, so if you went up and you looked at a dartboard, you might see a pattern that looks like this, where most of the throws are patterned around the bullseye because that's what people are trying to hit, and then fewer and fewer will be found farther out. Now, that's if somebody good is throwing darts, okay? But hey, whatever, right? So if some person walks up and throws a dart at the dartboard, based on the pattern of the holes you've seen from the previous players, where will this dart most likely land? Well, you might say close to the center of the board, and you would be correct, because that's where, based on this probability map, that's where there's the highest probability of finding a throw. Okay? All right. So here's the probability map. It's more likely in the center and less likely out on the outside. So in a probability map like this one, the higher density of the dots, the greater the chance of random dart throw. So here I have a model of a helium atom, okay? And what this is doing is it's saying, all right, helium atoms will have 2 electrons. So if we were able to look at where both of those electrons were at any given time, we might see something that looks like this. Okay, so if I put a trace on this, you'll see it starts to develop a pattern. And as I decrease the time between when I find these electrons, you'll see the pattern start to get more concrete. Okay, and we'll come back to that in a second. When we come back to this, you'll see that it's starting to get very blue in the center of this atom. And it's starting to fill in a little bit farther away. Now, they've put a cutoff here, a sort of arbitrary cutoff, but there would be a probability of finding like 1 or 2 hits out here. You know, that might happen. But you can see that most of them are going to be closer to the nucleus. Okay? And a lower density, a lower probability of finding an electron the farther you get from the nucleus. Okay? So one thing that's important to keep in mind is that each orbital can hold a maximum of 2 electrons. Okay? And they are described by their energy level or their shell. And the energy level or shell is given the symbol N, and their subshell. So for example, 3px. Now let's go back to the simulation here, and let's jump ahead a couple pages. So we saw this flat orbital here, which was the chance of finding an electron is the highest where the blue is the brightest. Okay, so that's a flat 2-dimensional representation of what's happening. Okay, now the problem is we don't exist in 2 dimensions, right? We exist in 3 dimensions. So what actually happens is rather than being like a flat circle, this is more or less spherical. Okay, and oftentimes what's done with orbitals is there's a cutoff. So we put a surface in, a solid looking surface, and we say inside of that surface there's some sort of arbitrary cutoff. Usually it's either 80 or 90% probability of finding an electron within that region. Okay? So here again you'll see orbital notation, and here's the primary energy level, or as we're going to call it, the shell. Okay, that's what this is, this number 3 here. And there's this orbital type, or subshell, which is this P. Don't worry so much about the X thing for now. We'll kind of come back to that. So my question is, what does the shell describe? Okay. Well, let's take a look at, here I have an orbital, and then I have an electron that I can kind of move around, all right? So what happens if I take this electron and move it from the 1s to the 2s? Okay, so here's the 2s orbital. Here's the 3s orbital. Here's the 4s orbital. All right, so the question is, what does that number, the energy level, what does that indicate? Well, that indicates the size of the orbital and or the distance from the nucleus. Okay, so my n equals 1, so the 1s is the lowest energy orbital, is a lower energy orbital. And then there's the 2s, which is a higher energy orbital. Okay, these are the closest to the nucleus, and these are all further away. And the distance is kind of related to the energy of the orbital. All right, well, what does this P thing do? Well, this is an S, that was a P, so let's move this around. So here's a 2P. Well, that's interesting. Okay, so that's something new. All right, so here's the 3S. Okay, there's the 3P. Oh, I see. Okay, that's interesting. And here's the 3D. Wow, okay. 4S, 4P. Oh, cool. 4D. Okay, there's a lot of good stuff going on in there. And 4F. So if you had to say what this orbital type or subshell describes, what would you say? Well, if you're really bright, you would say that the subshell describes the shape of the orbitals. Okay, the shape of the orbital. All right. So for each shell, there are n number of subshells. Okay, so in the first energy level, there was only one subshell. In the second energy level, there are 2 subshells, 3 subshells, 4 subshells. So in the 5th energy level, there should be 5 subshells, okay? Subshells increase in energy and are identified as S, P, D, and F, okay? S, P, D, F. So the super PDF, I don't know, you got to remember these, the S, P, D, and F. There are other ones, but we don't find electrons in the ground state in anything but an S, P, D, or F. Okay, and maybe we can talk about that later. Okay, each orbital is an orientation of the shape in 3D space. Okay, so we say that this 2P, this P orbital, is dumbbell shaped. Okay, and remember that that we're not in 2D space anymore. We're in 3D space. Okay, so if I have a dumbbell that's sort of in 3 dimensions, okay, I can sort of do this, where I have my X, Y, and Z domains, okay? And maybe I can draw a dumbbell that is kind of on the X-axis, but lines up on the X-axis, but it has parts of it in the Y plane and the Z plane, all right? And I could also do that where I have my orientation along the Y plane. And I can also do an orientation along the Z plane. Okay? So as it turns out, for the P subshells, okay, there are 3 possible orientations, because it's got this dumbbell shape. There are 3 possible orientations. And each of these orientations is a probability map, which means that each of these is an orbital. Okay? Well, the S is spherical. So how many possible orientations do you have for the S? Well, you have 1. It's just a sphere. Okay? Which means that there's 1 probability map, which means that there's 1 orbital. Okay? The P subshell has this dumbbell shape. Has this dumbbell shape. Let me go back down here. And it has 3 orientations. So it has 3 orbitals. Okay, these are the 2 that I want you to know, okay? The S is a sphere. The P is a dumbbell shape. Dumbbell shape. Okay? And the D has, you're just going to have to memorize this, I'm sorry. The D has 5 orbitals, and the F has 7 orbitals. So what would the G have? It would have 9. Okay? So that's kind of orbital basics, all right? And if I take a look at the energy of each of these things, okay, I start out with my 1s, which has 1 orbital, okay? And then my next highest energy would be the 2s, and that has 1 orbital, okay? Then 2p, which has 3 orbitals, then 3s, then 3p, then 3d, which has 5, okay? And there starts to get some overlap here, all right? We're not going to worry about that too much right now. I just wanted to show you that energy goes from lowest, which is the 1s, to the highest, which at this point is the 6d. That's the highest we're going to place stuff in.